So welcome everyone. It's a great pleasure to have our today's guest here for the QuMat seminar. It's Alexander Struk from the Rhein-Waal University of Applied Science in Kleve, right behind the border. Alex did his PhD in 2005 in Hamburg, working on electron-electron interactions in the integer quantum Hall effect. Then in 2006, he moved with a Marie Curie Fellowship to Vienna. And from there, he moved to Kaiserslautern as a postdoc, where he stayed until 2010. Then from this university position in Kaiserslautern, he moved more towards the applied science, which is the Fraunhofer Institute in Oldenburg, where he stayed for 2 years before in 2012 joining the University of Applied Science at Kleve. And in general, his interests have been, let's say, traditionally strongly correlated electron systems and mesoscopics from the physics point of view, and more recently thermoelectric properties, batteries, and so on. So things that have to do with energy conversion and these type of questions from a maybe more applied perspective, but also in the method development, as you will see here, machine learning and AI techniques applied to various things, also to data analysis. And so we are looking forward to hear in particular about the critiques in the nutshell.
Yeah, thanks Dirk for the kind introduction, and thank you all for giving me the opportunity to talk again to a physics audience, right? You know, once you have moved to the applied sciences, you miss a few things, right? One of the things that you can miss is certainly the exchange with physicists, right? Because that is something still special, I think, in the world, right? And so I'm very happy that I can present a talk here. And I was asked actually to talk about that title that Dirk has just cited and that you see behind me. And the reason why it is important, particularly for physicists also, to know about these things, might not be as clear as for other things, right? So no one would doubt that the knowledge of mathematics is important, right? But why machine learning? Why artificial intelligence? Save for the fact that we encounter it every day, right? So I'm not going to start the discussion about ChatGPT yet, right? Because I think we all had enough of that. But of course, artificial intelligence, machine learning are techniques and methods that are not easily going away. So in the scientific way that we follow, we need just to cope with that, and we need, of course, to utilize it as well. That is a great advantage if it comes to data analysis, for example, right? And with data analysis, I would like to address actually not only the experimentalists, but also the theorists, because simulation data, of course, can also be treated like any other data point. In principle, data is not just numbers. The data is much more than that, right? So essentially, we are letting in a whole theory of information and a representation of information that we have indeed in the computer sciences, for example, under discussion for years. But it is also transferring to the more fundamental sciences with quite some impact. And not everything is good in there, but certainly not everything is bad, right? And as with all methods, a thorough understanding of what you're doing is important, particularly because well, latest, I would say, since the release of TensorFlow by Google to the open world, right? We have very easy access to these techniques. Yeah, so this is not a nerdy stuff where you have to code things on your own to create algorithms that work specifically for your problem, maybe, right? As many of us experience this in their everyday research still. Machine learning methods in particular are widely available, are very well documented and easy to deploy, which doesn't mean that it's easy to generate knowledge from that. And that is partially the critics part that I would like to mainly put to discussion. I don't want to guide you into any perception there, maybe make your own mind about this and see what comes out there. Right. So let's maybe go right into it. But before that, yeah, Dirk mentioned this also. I'm from Rhein-Waal University. For those of you who have not been there, just take a look, right? It's really right over the border. Yeah, just located in Kleve, also in Kamp-Lintfort, but Kleve is closer from here, right? And these are just impressions of our campus there, and it can particularly in the summer be quite nice, right? Here's some data. I don't think I have to go there in details actually, but you see we are quite interdisciplinary here, right? So we have different faculties. I'm coming from the Faculty of Technology and Bionics, right, which is basically an interdisciplinary approach to natural sciences and engineering, right? So also in connection to each other. And that is something that is quite enjoyable actually to do teaching, research, and studying there. So yeah, but now let's get into the details here. Let's put it like this, right? So when we want to put criticism or praises of machine learning, we should be yeah, aware from a topical point of view. What are we talking about? And what we are talking about, for sure, is very difficult to define because there are, of course, many variants of machine learning techniques that you can employ. One that is maybe, or one definition that is maybe capturing the most of it is what I wrote in blue here, right? So learn properties of data without having to program them explicitly. This is basically a textbook definition when you Google it or so, right? And the thing is, how can you do that, right? So obviously this is where the word learning comes from, right? Because this is what we tend to do, right? So we basically look at something that is given to us, data, yeah, and we are making up our minds about this and try to basically make some sort of cognitive process to, let's say, predict what could be the next action, right? So, for example, if I look outside and I see clouds, right, I can maybe predict it's going to rain, so I better take my umbrella, right? Or at least a rain jacket, or something like this. Well, this sort of yeah, multi-scope perception that our brains can do, machines usually can't. So you need to tell them what to do. And there is basically the variant that you also do in physics quite a lot is you create a model and you use the model to predict values. And of course, if you want to have a good model, you need also to predict some values that you can measure and then basically feed them back to see how well your model worked, right? That is something that is still, I would say, the core of what is called supervised learning, although this has been invented long before the term machine learning itself, right? So if you think of how a Kalman filter works, for example, that is very similar in at least in some aspects. It's not entirely the same, but anyway. Modeling is one thing, and one thing that we are familiar with is, of course, linear regression. So we like to do that in physics. We measure bivariate, let's say, data, right? So we measure one, I don't know, voltage, yeah. So and then we measure a current, and then we look, are they sort of connected to each other? And then we see, okay, we make a scatter plot, and we see, okay, they basically run more or less in a line, yeah, depending on what your instrument is. And then you try to model this by just putting a line through it. And maybe this is a good starting point to see what machine learning is, and we will we'll get there. But before we do that, there is I just wanted to show you this yeah, kind of decision tree here, right? And this is from a nice book that is called Hands-on Data Science that basically gives a lot of examples like this. But well, I think I modified it a bit to make it a bit more explainable. So basically, how do you predict or forecast a value? That is basically the thing that you always have to ask, right? And if you want to predict one, then of course you can't do this just now, right? So I could say, after having spent a whole day in the basement, I could say, okay, it's going to rain, but I have actually no evidence because I didn't look at the sky. I didn't see any rain clouds. Yeah. So essentially, if I want to forecast something, I need to understand my system. Yeah. However, I can, of course, also just look what's around and I can try to detect patterns. I can see, is there some structure in the world that I see by just looking into it? This is the difference that you make between what is called supervised and unsupervised learning. Yeah, so supervised learning doesn't mean there's a teacher behind you, but in a sense there is, because supervised means you are basing your models on data that is given to you, right? There are two large distinctions. One is regression, one is classification. So basically, the social scientists would say qual versus quant, right? So quantitative prediction, which is usually regression, and then you can also predict categories, and that is basically you order your categorical variables into bits, and that is what is called a classification. Yeah. So I mean, if I would make a classifications of people physically present in this room, right? And I would basically divide them into males and females, right? So I would have a count of about I don't know how many males there are and 0 females, right? Which is something that I could learn something from, right? But we are not going to do this now. No. Obviously, females would be very welcome here. Yeah, and so basically what I will focus today on is supervised learning, because this is for our science probably the more relevant case, although probably there's a lot of critics. Yes, please.
Yeah. Distinction between supervised and unsupervised learning. The way you explained with the supervised learning, if I understood correctly, it's about the data you have from which you supervise the machine. So now I'm wondering about the unsupervised part. Couldn't I just cut the data in half and then use half of the data to supervise learning for the other half?
Yeah, that's a very good question. I was maybe a bit too rushed with this. No, unsupervised learning means basically that I use algorithms that work with data that is given without any I would say predicaments that I do, right? So, for example, if I do regression, then I already present a model that I want to basically adjust to the data that I have. In unsupervised learning, of course, this is also based on data, but it goes maybe more towards making your own analysis out of the data that is given to you. Right, without actually prescribing something that is in the end giving me the forecast or something like that. Yeah, but indeed this should be one should be careful with these words.
It's roughly fair to say that supervised learning, then the supervisor supplies the labels. And unsupervised learning.
Yeah. That is exactly. This is already the technical term for it, right? Indeed, this we will talk about, but that is indeed the precise definition. Well, we will have this in a few minutes, and then it probably becomes more clear also, right? But indeed, well, we can do it also now. You determine. Actually, I think it's even coming on the next slide. Yes, it's exactly there, right? So basically. You come from statistics more than from computer science, so this is something that we can actually think about. So in statistics we have variables, independent variables usually, right, that we can tune, right, and then we have what we call dependent variables, which basically react in its values to the changes that we do to the independent variable, right? And then, of course, we can do transformations in the widest sense to these dependent and independent variables and try to figure out a relation between them, an association even between them. Correlation is for linear regression that what we need, right? So basically measuring, finding a number that represents the linearity, for example, of the two data sets. And basically, in machine learning, you do more or less the same, right? But you do it with different other words, and that makes sense also. So basically, the variables you call features, because a feature can be a number. It can also be a name. Yeah? It can be basically anything that carries some sort of useful information. And modern machine learning techniques use all of them actually to do something with them, right? So, for example, text-based analysis, as done in ChatGPT, for example, right, is a very, very highly advanced method, but also research subject these days, right? So that you basically work with more or less natural language. So something that we in physics are not so used to, right? So we are using usually numbers in it, right? And you mentioned the label already, right? So basically the label is essentially what the dependent variable is. Although when we talk about numbers as in the regression, if you think of classification processes, the label can be something even non-numerical. It's just a category, right? And indeed, in supervised learning, you basically prescribe what categories are there, right? Whereas in unsupervised learning, if you want to really put it down to very simple terms, you basically create the labels on your own, or you suggest labels that you can use. You can change them later on also, right? And then there is, of course, also combinations of those, right? And where you basically can use both approaches to some extent. Yeah, but for example, we will see this in an example for classification. You can also map numerical data, for example, to a certainly different label. Yeah. To be honest, you have seen that also when you count the types of cars on a parking lot, right? So you have a Ford, and you have you have a Tesla and some other car brands, right? Then you can count, of course, how many of them you have there. Make a histogram out of this, or rather a bar chart, right? Histogram, maybe not so much, a bar chart rather. And then you also have done your first classification based on supervised learning then, right? One thing in which I also will not talk about, but I would like to mention is that it's basically probably mainly unsupervised learning is data mining, right? So you try to basically get patterns out of given pools of data, right? So you of course try to predict also outcomes from that, right? So you try to understand your data set, right? And you try to extract also more than the data is telling you. This is basically the mining thing, right? So if you basically pull out a piece of load out of a mine, right? It is not quite usable for you, but you can basically break it off and then basically get away of all the load, right? So take the ore, remove the load, and then you have the metal inside, right? And that is in fact something that that you can do also with data. That happens a lot in the context of big data, as it's said sometimes, right? So big data meaning you record data from everywhere, right, and put it all in, right, and then you try to contextualize these data points that you get to get more information out of that, right? And that has also some risks, as we know, right? So the transparent person is something that no one talks about these days anymore, or at least not as much as a couple of years ago, but it's still out there, right? So basically creating knowledge from data sets. But just to go a bit more into the thinking process here, what is regression? Yeah, so regression is something that we understand, right? And you start from a variable was the voltage, I think, that I just created, right? And you measure the current, right? And then you can basically fit your model to it, right? So in linear regression, you basically assume there is a linear or a affine relation. Yeah, so you have a certain intercept, and then you have a slope, and then you can basically model your data set to some accuracy out of that. And using the data points that you have, you can basically figure out what the best slope is, right? So basically a least square analysis, what the best slope is and what the best intercept is. And then you have created your model. And of course, within limits, you can use it to predict the outcome of the current if you measure a different voltage. Oh, that's possible. And it's very similar. We can do that also, and that is maybe not so clear to everyone, to actually a whole set of independent variables. Yeah. So if I have not just the voltage, but I have measured also a couple of other features, as we would call it, I can of course try to figure out a linear form that projects the values of all these features onto one singular value. Yeah, if you do this with two features, right? So you have something like a times x plus b times y plus c is equal to 0, something like this. That's apparently the equation of a plane. Yeah, so you cannot only fit lines, you can also fit planes using essentially the same principles. And if you want to have even more variables, yeah, then you call it a hyperplane because you can't visualize it, obviously, right? But you can still find linear forms that are used to essentially cover multidimensional spaces. And I just want to show you briefly how this works, only to get your minds ready that the things that where the machine is actually learning, right? It's not so difficult to grasp, at least not for regression models, right? Because you start with something that is very much known to you from linear regressions for a line. Right? So I showed this here. You just write down a linear form, and you have, of course, n plus 1 parameters. Yes, if you have n feature length set of length n, you have n plus 1 unknown parameters. Yeah. For n equal 1, you have the intercept and the slope, and for n larger, you have multiples. I called them theta here, right? And you have this form here actually that you have to figure out. Yeah, the x's are your features. You know a few of them, and you know also a few outcomes of h for it, right? And the question is now, how do you figure out what these thetas are? And as in linear regression for a line, most of you hopefully remember that, right? You do something like, you work with the least square error approach. Yeah? So you basically, first of all, calculate essentially the mean square error, right? Half the mean square error, as you see, there is this little factor 2 there. That is just for convenience, but as you know, it doesn't matter in the end. But once you have written this, so the yi's, of course, are in this. This is basically what you call your training set, right? So you know data points xi, feature x, and the label, the according label to this, right? And so you know for these couple of points, yeah, you know the truth, so to say, right? So, or at least what you measured, and what the data tell you. And then you can, of course, write the error. Well, if you plug this into your model H, right, for a given set of thetas, of parameters, take the difference, square it, sum it up, and divide it by the number of data points that you have, then you have the mean square error, of course. Yeah, and then you just need to minimize this. This is quite a simple question. So you take the first derivative in all of the feature parameters, right? So the linear parameters that are in the model in front of the features. And you just derive this with respect to each of them and set the resulting function to 0. That is just basically curve sketching and multivariate curve sketching. I just wrote it down here. We don't have to go to the to all the details, but what you see in the essentially in the last line. I don't know if I can show this here also for the no, it doesn't seem to work. But if you see the last pink line there, this is essentially the outcome. So basically, you can write this something like a fixed point equation. Yeah, so you get an equation of or a set of equations to find the roots of this linear problem here. And in order to solve this, you can essentially transform it into a 6-point problem. So essentially like Newton's method, right? Machine learning, you rather work with these setups here. There are multiple variants, of course, but in the easiest case, you write it down like this, and you introduce what is called the learning rate. Yeah, so this is also one parameter that you quite often can tune, right? And that is basically similar like in Monte Carlo simulations. Actually, you don't want to jump from one solution to the other too quickly, but you rather want to evolve. So the way how you improve your estimation of the parameter is done in a gentle way, and this you can essentially control. But eventually you get your set of data points, and then you basically have found a set of linear parameters that give you a linear model that you can use for prediction. So this is something that we are quite familiar with, right? But what you essentially do is that you apply this in a typical machine learning problem to a huge set of data. Yeah. So I will later on show you some results from a recent research project. Yes, please.
Sorry, just having any questions. So one is like very many, like in this linear regression sense, in which phase does machine learning come into play? Because linear regression sounds like something I could do without. That's exactly my point. The machine learning part of it. I mean, this is the most simple way of machine learning. Yeah. So there are more complicated versions. We will see some of them later, hopefully. But this is basically the starting point, and this is a very simple method of already starting this learning process. Yeah. So this is basically all I say. You apply a mathematical method to find a model that resembles your data in a perfect way. And actually, linear regression is the easiest way of machine learning that you can put. Yeah, I mean, there's really no more secret to this. Maybe the art in this is rather this learning rate, right? Because obviously, if you just have a line to fit, no problem. Yeah? So everyone can do that. Every software can do that. Even Excel can do that. And yeah, which is basically not a machine learning tool per itself, right? But if you in the end can use larger data sets, then you run into all sorts of problems, because the more parameters you fit, the more difficult it might become, right? And not so much in the linear case, but there are, of course, also non-linear methods later on and so on. And so basically what you do is you do this in a more empirical way. Yeah, so you control your learning rates and see how far you get with this. This is probably also the part where the learning really is there, because also the machine remembers what is the best way to start and so on. Yeah, at least there are formulations of this. Yeah, this is of course something that is if you want to characterize your algorithms, that is probably the way how you should go, namely by checking how accurate is it, how much does the training take. I will tell you that this is basically the thing that is usually the most critical part, because if you have really large data sets, this just takes time, and if you have to do multiple runs, sometimes you really get into an organizational problem in the end, right? Unfortunately, the linearity for this process is not always given. Yeah? Ideally, it is. Yeah, and then of course, the more parameters you have and the less features you are given, the more problematic these fit
fits become. I mean, we know this from linear regression already, be it multivariate or univariate, that the error margin is quite, can be quite large, depending on the quality of your underlying data set. Basically coming back to supervised learning, so as as regression is in that sense, is now to make this a bit more general. So can I predict, let's say, first of all, discrete values, discrete variables out of something that is probably even non-numerical? So can I basically find a way to model things? And that is actually one method that is also nowadays very often implemented, and that is the basically what we call classification, the prediction of non-numerical labels. And we do this, of course, by mathematicifying them, right? So what else do we do? And so a classic point, let's stay with the weather, right? So I can measure all sorts of values, temperature, pressure, humidity, whatnot, right? And from that, I can try to predict, will it rain or will it not? Easy question. This is a yes or no answer. So is it raining or is it not? Right? So you know, from where I come, from northern Germany, it rains at every weather, right? So it's no use to predict. But well, you can basically put it down like this, right? And if you do this basically formally, you say you put a continuous variable. So it's either yes or no, right? Obviously, if it's continuous, I can always discretize it. I just choose from the whole set of just two, and then I just have to construct a function that maps from the data that I have, right, to a continuous variable here, right? And as I have indicated here, linearly, this is not possible, because if I have a linear model, in principle, I have an unbounded model. The value that I get from this model is not in the range between 0 and 1. This depends entirely on the features that I put in, which I can't control. Because if I make a prediction based on the data that I have no limits. So mathematically, I'm lost here, right? So linear models not so good. But what I can do is I can use a nonlinear function here. So some of you recognize, maybe if you turn this by 90 degrees, you have something like the Fermi-Dirac function, right? Which essentially discretizes also. You have occupied quantum states or non-occupied quantum states, and then if you have temperature, you smear this out a bit. Similar thing here, right? What is often used is this sigmoid function, as it's called, right? The function form is not so important here, right? So you all know how to deal with this, but it has the nice property that it's bounded. So it is somewhere between 0 and 1, and so I can say, as I do it with final temperature Fermi function, if it's larger than 0.5, I assign it to occupied, and otherwise I assign it to unoccupied. Same thing here with does it rain or not? It's either yes or no. And so you see, you are then, I will speed this up a bit, but anyway, you are using the same models again. So you say, okay, I put in my feature matrix, if you want, right? So my list of feature values, they all have these parameters, right? And I encode them in this function. And then again, I try to fit parameters based on the training set that I have. So basically based on the data sets where I know if I have this temperature, this humidity, these data values, then I know it rains for sure. Right? Then I have measured the next day, I have this set of values, it doesn't rain. And I produce a couple of thousand of them, and then I can start to determine the parameter of my sigma model here, of my sigmoid model. I can then, of course, also formalize this in a more or less probabilistic way. And from this probabilistic way, I can then, I'm not going through the details here because it's not so interesting, I think, but we can talk about this afterwards. I again do some sort of a maximization here, right? Before it was a minimization, but here I would of course find the likelihood of my model to be as true as possible, Yeah, and the likelihood I can basically, as in any maximum likelihood method, formalize as a product of probabilities that that the data set actually fits the model, and usually conditional probabilities. And if I work with this, I get something like a binomial distribution approach, and from that I again can figure out a learning equation here, right? So I again find this this equation that resembles quite a lot the linear regression, but this time actually for even non-numerical variables, as long as I can label them numerically, and can from this decide whether I am in or whether I am out. Yeah, does it rain or does it not? Yeah, with this, I would like, I mean, obviously, this is not all that machine learning is. Yeah? This is just the thing that is the easiest approach, right? And since there wasn't so much time today, I thought even this selection can be used to achieve quite a lot in the fundamental sciences or science questions rather. And one thing where we have applied this is in a project that is actually running a bit longer because of the pandemics indeed, but it was essentially assigned for this period, and we tried to figure out essentially what we can do in order to improve sensor technology for detection of bacteria. So you could say, what is this good for? Well, it's good for if you have a food processing chain, yeah, and you have, let's say, conveyor belts where a lot of food is on there, right? And you know specifically if you deal with meats, the spoilage rate is quite high, yeah, because the meat, of course, is easily infected by germs and bacteria, and you want, of course, in food processing a very clean chain, so you want to know as quickly and as accurate as possible what sort of bacteria do I have on my sample. And the classic way is you wipe it, yes.
Sorry, in the previous example,
yeah,
the outcome was discretized, right?
Yeah.
Was categorized.
Yeah.
But what happened with it, where the data set is also categorized, like, I don't know, in social science?
Yeah, then you have, exactly. Then you have essentially do the same discretization process also to your feature input. I mean, in a sense, this can be quite difficult because you need to, first of all, model your system appropriate. Yes.
Exactly. And
Yeah.
you have maybe correlations between.
Absolutely. Yes. And these are things that where you have to develop specific techniques, right? This is also this is a thing actually that we can happily discuss afterwards, because this tells us already quite something about the usability of certain methods, right? Because as you say, if you have understood your data set quite well, and you are trusting in the sense that you know what has happened to your data there, right? If you have devised the algorithm, can you really use it for the next data set? Or do you have to do the same analysis again? Yeah? So there are pros and cons, and not every learning model actually works appropriately for even quite similar sets of data. Yeah? So there is specifically, if you are basically researching into the blue and can't really project back. Yeah, so I mean, neural networks, for example, do this in a certainly in a somewhat different way. They have essentially methods. Yeah, so in the classical neural networks, it's called the backpropagation, where you essentially make an error analysis later on, send it back, and then even if new data sets come in, right? So you continuously try to improve your neural networks, right? Modern variants use essentially some sort of convolutions there with which essentially have the same purpose there, but it is certainly not generic to say it always works like this. Yeah? So you have to basically the preparation of your data is very important to make the algorithms work also in a proper way. So, and this is certainly one of the problems that you easily can encounter. Yeah. Anyway, here let's start from something very simple and very understandable, because what we discussed so far, these so to say classification out of a numeric assembly to a again numerical assembly, so essentially 0 or 1, yes or no. This is something that we used basically to improve these sensors here, and the idea was indeed to make this detection quick and basically it's possible in real time. We are not quite there yet, but I think it will happen because making these biochemical swap tests take time, and of course in any meat processing and food processing, the degradation and the infection with germs happens very quickly. Right, so you anyway can just do estimates, and you want them as time accurate as possible, of course. And the one thing that we thought is helpful, and proved to be this, is spectroscopy to detect spoilage. Well, you can think of a germ that sits on the surface, and you can take the spectrum out of it. And then you get, in this case, it's a Rhein-Waal spectrum, right? So it's essentially, we shoot a laser there, right? Let the molecules vibrate, right? And there's light sent out. I don't have to tell you what this is, apparently, right? So that is good. So we get some sort of Rhein-Waal spectrum out. And bacteria are quite Rhein-Waal active, many of them, and they have quite clear signatures. But if you just look at this, you see, is this dark spectrum really different from the gray spectrum, apart from some shift, some oscillation? What is noise in there, what is not? For human being, impossible to detect. Yeah, is this noise? Is this so our minds and our resolutions, the sensors that we have, the eyes, isn't good enough. The machine, however, can deal with these differences if you just have enough of the spectrum. So we used, I think, more than 100,000 in the end, right, to just see what is actually common in these spectrum. And the first thing that often fails is, of course, what is called the principal component analysis. Yeah. So basically, this is just a little game here, right? If you play tic-tac-toe, you want to create sequences of crosses or dots that make you win, right? And of course, in this easy game here, you just have 8 possibilities to draw a line of equal systems. So basically having a good combination of features in our notation. Yeah. So you can put basically a punctual ID to it, right? 0 is the circle, and 1 is the dot or so. And then you can basically give a matrix, a feature matrix out of this. You can, of course, also try to do this in a 3D cubic system, right? And you have then a couple of 3D boards basically stacked upon each other, right? And then you have, of course, a multitude of good solutions. Yeah. Which one is the one that you remember best if you want to train, basically if you want to figure out what the best strategy is. And that is something that you can do with a method that is called the principal component analysis. So for the theorists here, right, so the randomization group density matrix randomization essentially is such a PCA method, right? Because what you do is there you diagonalize your density matrix, you select the best eigenvalues that contribute most to your rate function, you cut away the rest, right, and work with a much smaller system then. Same thing you do here, only that you use your feature matrix. Yeah, so you say which feature is best and represented by its eigenvalues there. And this is essentially what you can do also here. So you don't work with your feature system, but you work with entire combinations of them. Yeah, and in many cases this is already enough, but it turned out for our system it wasn't really, right? So even doing highly advanced forms of PCA were in the end only good to say not necessarily to classify which bacterium is the best, but although for some that actually worked quite nicely, but rather as a dimensionality reduction that we used to start our analysis with, right? And so in the end, what we ended up with are convolutionary neural networks, but also the classical methods, basically classification and regression. Yes, there's a bit more to classification. And you mentioned already one thing that can be done is also things like which is called k-nearest neighbors. Yeah, so where you essentially try to find from the properties of features and what their distance to a feature is that you know has a specific label, and various other variants. To be honest, we tried them all, and most of them, and it came up in this case that these neural network approaches were good. But in order to understand what we did, it's not so much important what the actual method is. But the idea is that you let the machine look at basically spectra, and you know, of course, you can prepare a sample which has a certain as we call it, total viable count, so a certain number of bacteria and of a certain type, and then we can basically measure Raman spectra and try to see how they change when you change the concentration of the bacteria or the bacterium type, right? So we have a combined classification and regression problem here, and what the neural network does is that it essentially detects features, transforms the features, and then essentially narrows them down so that it says, okay, when I get a different set data, a different measurement, right? I can use the model that was created by this analysis to extract exactly these features and then make the classification.
So first step is to run a PCA.
Yeah, we have tried that. Yeah.
And then you feed it to the.
Yeah, you don't have to do that. For us, in some cases, it turned out to be helpful to first reduce the dimensionality of it. Yeah.
Does it actually do better than Fourier transform and feeding it? I'm just asking because.
Yeah, you are free to ask. Of course, I'm just thinking. So to be honest,
there's a reason I'm asking.
Yeah.
It's like I also did. Machine learning project at some point.
Yeah.
We took snapshots of spin configurations and then we let PCA decide like what's the best way to represent data, and it found that Fourier transform is the best way to represent the data. So here I also have the feeling like with spectra, Fourier transform is a very natural.
Yeah, to be honest, we didn't try that in the first place. I can't remember if we had a reason not to try it. But it could it certainly worth a try. In the end, the PCA, though, the dimensionality reduction in that sense, isn't the core step here, right? Because for the classification, it also in the end worked also with full spectra actually, because also this is something that worked. PCA, though, is in spectroscopy a well-established method. But this may be a good idea to think about Fourier as well, but maybe someone has done it. So I can't honestly remember that we did it, but why not? Yeah, that's certainly also. Yeah, it is cheaper for sure. Yeah. But in our case, the computation came into the neural networks rather than into the PCA. That this was not the crucial part actually. Yeah. But anyway, it's a good suggestion for sure. Basically, what I can end you up with is maybe the error margins that we got here, right? So here you see different. I mean, this is basically all classified. This is why you have these weird labels here, right? So the actual substrate I can't disclose here, but not that I know it actually. So, so you see, when we worked here with 20,000 samples, right? What we did is actually something that is not advisable to do. Yeah, so we split our data set into a training set and then a set of data that we try to test with. And this came out of practicality, because if you have a large project, you know, communication is important, and not everything is always doable. And that's not a critique of the project, that it's rather it's just practical work, right? And what you have is indeed that you essentially test your basically your model with the same data that you use to create it, which is usually bad. Yeah? So for that reason, you had to, we had to add also always some data that were freshly taken somewhere to see if the model is in a sense transferable, right? If I would do it better these days, I probably would have done this in the first place. We found though that in the cases where we did it, the results were still comparable to what we have. So which is in our system also understandable, I would say, because these things were quite isolated so far. Yeah? So we didn't really work with the real world Dirk stuff, but with something that was very well prepared. So in that sense, these results were quite trustable, and you see that we have here an accuracy of detecting the right amount and also the right type of bacteria with pretty high success rate, right? Here basically expressed via the root mean square error also, right? So that is something that works, for our detection purposes quite nice. And basically we tried also different models, and then of course data augmentation sometimes also is needed. This is another machine learning techniques also. Data augmentation sounds to me always a bit like cheating. Yeah, so you basically create additional data sets based on the statistics that another data set has. Where you think, yeah, exactly, this is what I thought, right? It's like, but isn't it? Yeah, well, you don't pretend though that you actually have another data set, but you essentially give the machine a bit more relaxation to play with, right? So it basically, if it learns statistically, right, then it doesn't really matter basically where the data comes from, as long as it follows the statistics. However, you of course can add only very few of these samples. You can't basically just take one data point and then augment it by 3 million computer generated ones. That wouldn't work, right? But these sort of things actually sometimes trigger the machine to think, yeah, so to learn into the right direction. But to be honest, this is something I'm not too proud of because it's a bit of alchemy in there, right? But anyway, this was at least in this context quite successful, and also with quite simple method. I didn't specify, mainly for time reasons here, which sort of spectroscopy we did. We were very happy, I think, with Raman. Fluorescence also worked, but not so good. But still, this is quite adaptable also. And what we still want to do is basically make this into really a machine that is usable in the field. We built though a little demonstrator that also produced some nice results. Right. Main problem of this was that it actually couldn't work yet in a moving state, so it had to stop when doing the spectroscopy, because otherwise you have some sort of Galilean shift or something like in there, right? Which is not so. But yes, we can take Raman spectra, and the Raman spectra are varying in different contexts. Yeah, so the material of the conveyor belt plays a role, the type of food on it plays a role, and of course the type of germs that you have. It is still a challenge actually to figure out the right way to comprise this huge set of data that you take into something that is trustable and reliable, right? So because in the end, having basically a better estimate for the best before date, or even for essentially removing this from the food chain at all, is still an urgent, really pressing thing. And yeah, this is at least a step towards it. With had already some progress there. Yeah, I think I'm at the end here because unless you have more questions, of course, because time is essentially over already. So the thing that I wanted to raise here is essentially how much can you actually tweak this? Because so far, it seems like machine learning is producing data out of nothing. Yeah, so it is producing models essentially just out of data points. But is this the same as for us to generate actually knowledge and understanding? I mean, in different communities, you say already, why do we need simulations anymore? We can just put machine learning onto experimental data, and then we get our models, and then we are happy with this. Well, I tend to disagree because there is essentially what machine learning can do is create models that you can test and treat and improve and everything. Yes, and these models are useful, no doubt. But it can't generate theories. Yeah, so if you want to understand what there's, I mean, the social scientists, for example, like to talk about the data generating process. The data generating process is essentially, in our case, a natural law that is beyond that. And well, the data that we measure in physics, at least, are usually based on the action of natural laws. Yeah, in social sciences, not so much. Yeah, so because the laws there are not, there are maybe laws. Yeah, so I think the social scientists community isn't so sure about that. As people think there is the free will, right? So maybe it's there, maybe it's not. Maybe this is also social interaction. I'm not a social scientist, I can't say. However, what we can do is certainly figure out models. Yeah, as you presumed already. But these models are not theories. They don't tell us how this data generating process actually looks like. It just tells us in which order and in which way it produces the data. Something that shouldn't be forgotten, actually. Yeah? And we see that also with highly advanced artificial intelligence things. If you look into ChatGPT, for example, right, this thing answers you almost everything. Yeah, and it basically bases this on a huge and vast pool of data that is available to it. But it doesn't create a theory for us. Yeah, so this is still our job to do. And yes, I'm not saying we shouldn't use machine learning or even artificial intelligence at all, right? Because it is a new way to treat data and to improve basically the understanding of data sets. Yeah? And this always has been, to an exact science, one of the most prominent evidences that you can get. Yeah? So in order to check your theories. But there is essentially no such theory generated out of this so far. But we have a very advanced and high way of producing good data analysis. That for sure. And as I hope to have demonstrated, sometimes with methods that are not so difficult to grasp, right? But that still can be applied in a proper way. Yeah, with this, I shut up and let you actually take over the discussion, and I'm happy to stand for questions. Thank you very much.
Any question or next?
Next to them that were already there, which is better. Yeah.
I would have a question, like a straightforward for the unsupervised learning. So it somehow reminds me a little bit of the problem in psychology with disability crisis, where basically if you have less, like if you make a survey and have, let's say, 10 people, and now you allow like 20 labels in machine language terminology, then you're guaranteed to find some correlations. So if you have more allowed labels than data points, so to say, then you're basically, you can be sure to find some correlations. And that seems to be a similar thing in unsupervised learning, because if you don't fix like the labels, then
Yeah,
there seems to be an infinite.
I think not fixing the labels doesn't mean that you have free choice of for the machine to generate them. I mean, the advanced algorithms take care of that. Yeah, I think and to some extent, though, right? To some extent, I mean, all of these things, specifically also with neural networks, but I think also with I'm not so much so deep into unsupervised learning to be honest. But from what I understood is that you have, of course, always the possibility to basically take exactly the wrong term. I mean, there are methods to basically prevent it as good as you can, but this is not 100% certainty. I mean, the thing also with supervised learning is even you have a high sensitivity to false positives. Yeah, so basically, once you have basically identified false positives, right, and then network, for example, back propagating this in the wrong way, then it gets even strengthened. So that in the end, your network can be based on totally false roots, so to say, and always tends to give wrong labels out there. Yes. That is something you need to take care of. Oh yeah, please. First.
Just continuing in that direction. So as you say, like somehow the like with the unsupervised learning, we kind of fixed the problem partially to some degree. Could one try to transfer that to the psychology?
You need to ask this to the psychologist. I think I would say no, because I think this is also not perfectly fixable in a sense, because the problem you always have if you create a false label or if you just create too many labels. I mean, you can this kind of doesn't work at the end, right? Because you, as you say, you always get dependencies even if there are none. Yeah. So. But I'm not an expert in psychology. I would be very careful with that. So yeah. So yeah.
As a side comment about the number of appropriate number of labels, there's a nice trick one can do. Yeah, to give you an idea for just from normal linear regression. So you have a 1D data set, and you want to know if you're supposed to fit it to a linear or quadratic or cubic or whatever thing. Yeah. A nice thing you can do is you can take half of the data. It's kind of like training with supervision. You take half of the data, you fit it to all kinds of different polynomial orders, and then you apply it to the other half. Yeah. And then it becomes very clear which is the appropriate one to choose.
Yeah, I mean, this is exactly the method I just described, right? So yes, that is a common trick that you do. You split your data set, because the advantage of this is why why it's regularly done is that it's the data coming essentially from the same process. Yeah. So if I have taken on one sample, I have taken 20 spectra or 20,000 or 200 or whatever, right? And I say, okay, I'm using 70% of them. The other 20% I put aside. I've randomly chosen them, and then I can use them to test if I was doing any good. Yeah, that's true. On the other hand, if I have made a wrong label, then of course, basically, I just check for consistency. I'm not necessarily checking for truth. This is the danger. Yeah? And that is essentially also the danger that you pointed out, right? So what happens if I have too many labels, or if I have too less, or if I have the wrong ones? Yeah. Also that is a problem, and this is actually that you probably have to counterweigh with the right approach in your thing. Although there is a vast amount of research going on at the moment. I'm not pretending to know each and every of them, right? Also for very specific fields, right? So, I mean, I recently did look into text processing indeed, right? So basically natural language processing, and it's almost pointless if you have not at least a linguist in place that actually understands what the language is actually producing and how people actually form words and put words into context, right? Very delicate subjects. It's extremely fascinating also, right? But it's not something easy. But it comes back also to something that scientists know for ages already, right? Before you make conclusions, you need to understand your data. Yeah, so you need to understand where it comes from. No one, not even the highest machine learning entity, can help you losing that, right? Or can replace that in a sense. Yeah? So you need to understand what you're doing. You need to make consistency checks. You need to basically, and this is in my humble perspective, things that only humans these days can do, right? I mean, you can make consistency checks with a machine, right? But basically inventing the things and make even the counter test, yeah. So basically bring the thing to fall, yeah. With the classical falsification approach is something that still is very, very useful and helpful. Yeah, so to see how good this works.
So question maybe related to that. So for unsupervised learning, is it thus maybe advisable? Let's say you want to run unsupervised learning in some data set. Is it supervisable to go from, say, few neurons, few layers to more, just to avoid essentially overfitting?
Yeah, the overfitting problem is of course there. I mean, I can just in this case, I'm really not the expert, but I can speak from experience that this was rather a minor thing. At least for the project that we didn't see any significant thing. We saw some changes, but I wouldn't be bold enough to say this is really doing it. But of course, having more convolutionary layers.
Probably,
yeah, can I help?
Yeah. Get more patterns. Right?
Yeah, you get more. Exactly. Yes, exactly. That's the point. Yeah, and that can of course also help. Yeah, yeah. Mm. Yeah, overfitting is essentially a problem, of course, specifically if it comes to models with a lot of parameters. Yeah? So this is basically the sort of overfitting that we also know, right? So of course I can fit. Just probably because we mentioned the example. Yeah? If we do a polynomial interpolation of degree 105, I can fit anything with that, right? I still don't learn anything about my data set, right? So because I make the next data point, and it's certainly off because it's all overdetermined, right? So essentially, working with low order models still is very advisable, I would say. Yeah.
That's probably also why it's good to do PCA before, because then you're essentially
Yeah, of course. This is the big crux in it. On the one hand, you need a lot of data points. Yeah, so a lot of them, right, in order to get good results. On the other hand, the more the larger each data point is, so the more features are included, the more problematic it becomes because the easy model fits and usually don't work very well. So you need to reduce a bit in that sense. Yeah, although. It depends. You can, it's still a bit of try and error. Yeah, so don't tell this to the computer scientists. They probably disagree with this. But from my experience, yes, it's a bit of try and error also to figure out what the best way to go is there. And to understand your data, so to know this can work and this can't work. Yeah? So, I mean, we have as basically the physicists and the engineers who were doing this sort of analysis, we have regularly interviewed the biologists who had to explain the features of the spectra and the bacteria to us, because otherwise we would have run into this trap for sure. Yeah. So that is still quite advisable.
Yeah.
Oh, very thoughtful.
It actually relates to a previous question by Lars about the Fourier transform. So you said then that the Fourier transform would be, of course, computationally more efficient than using machine learning. If that was the right thing to do.
No, I think this was basically for the well, he suggested this, but this was basically for the PCA also, right? Because. Because I mean, what PCA essentially does is an eigenvalue problem exactly. But what Fourier does is some sort of a filter, right? So basically you basically integrate out the components that don't play a role, right? That's another method of reduction, right? This is something similar you use also in data smoothing, for example. right? So that is, I mean, if there are various filters, I mean, the statistical Goulet filter, for example, works essentially in a very comparable manner, right? But of course, I mean, using orthogonal functions like in Fourier coefficients, specifically if you have some sort of periodicity in there, which apparently the spectra you have, right? Then you basically can filter out all the signals that are not having high Fourier coefficients. That's certainly a advisable method. Yeah. I was just saying, I can't remember if we tried that. Probably not. Yeah, but this I'm not. But this is my bad, not a bad of the method.
So just in the context, like the question I would have is, so if there is like machine learning methods to solve the problem and non-machine learning methods to solve the problem, is it the case that always the non-machine learning methods can be computationally more efficient than the machine learning ones? So or is sometimes the machine learning
I would say this really is data dependent. Yeah, this is very data dependent. I mean, you can of course also in machine learning go into all the stuff that we did in numerics already over the last century, essentially, right? So so if it comes, I mean, to be honest, machine learning has a lot to do with statistics combined with linear algebra. Yeah, so you have a lot of matrix operations to do, you have a lot of statistics to do, and both can, in some case, nicely be parallelized. Yeah, so basically it's the same as if you do matrix operations in density matrix renormalization or in exact diagonalizations, right? So if you have block matrices, right? So you can of course diagonalize them in parallel quite easily. So you basically win something in time. But I would say this depends on your data set and your data preparation also. Yeah, so making these things, specifically these dimensionality reduction before, also using methods that are not entirely based on a machine learning technique, absolutely makes sense, because the better structured the data, the easier it is actually to get models out of it. Yeah, yeah, for sure.
Okay, so I suggest that there are further discussion points, then we can proceed in front. Yes, thank you.
Thank you very much.